Okay. Let's see here. Got to talk about the peptide bond. It's been a while since I thought about the peptide bond. Let's see, how does it go again? There's an oxygen, and it's double bonded to a carbon. And that's, then there's a single bond to the nitrogen, and then there's amino hydrogen attached. So we got a carbon double bonded to an oxygen, and that same carbon is also in a single bond with that nitrogen. Double bond, single bond. Okay. But wait a minute. There's something not right here. I see something. What? I can't believe it. Everything I've known and taught for 14 years is a bunch of crap. Luke, come here once. Can you believe this? Says here that the carbon-oxygen bond is actually longer than you would expect otherwise for a carbon-oxygen double bond. It's 0.02 angstroms longer. That means it can't be a pure double bond. Shoot. What are we going to do? Oh my. It also says that the carbon-nitrogen bond, which I always thought was a single bond, is shorter by 0.13 angstroms. What can that even mean? Here the fate of the entire world rests upon my knowledge of a peptide bond, and I'm confused. How can you have a double bond longer than it's supposed to be and a single bond shorter than you would expect it to be? What are we going to do? Think, Henry, think. How are we going to get out of this one? Double bond longer than it's... How can it be longer? Single bond shorter? It's almost as if the double bond has single bond character. And the single bond between the nitrogen and the carbon has double bond character because it's shorter than you would expect for your normal garden variety carbon-nitrogen single bond. Think, Henry, think. Yes. Take it anymore. Oh, resonance! The peptide bond has resonance! That gives partial single bond character to that carbon-oxygen double bond. Yeah, I think that could be it. And then carbon-nitrogen single bond is slightly shorter, so it's like it's got double bond character. You know what that would mean? That the peptide bond has a planar geometry. It doesn't revolve around the single bond. The carbon-nitrogen single bond can't resolve because it has partial double bond character. I can't believe this. I don't understand proteins, and I have to teach about them. Well, it's that time again. Another video. And this video is going to be dealing with peptide bonds. And hopefully by the end of this video you'll appreciate how the peptide bond and the geometries associated with it and the restrictions of movement, things like that, help define the possibilities when it comes to secondary structure. So to begin with, just as a reminder, peptide bond is the bond that's formed when you get the condensation reaction that joins two amino acids together. I mentioned this early on. So two amino acids come together and water is given off, and that forms this bond. And a peptide bond is really just a type of an amide bond. An amide bond is comprised of a carbonyl connected to an NH2 or something like that. So this is an amide bond. And what we will see is that what can happen is the lone electron, whoops, hit the wrong button there. The lone electron pairs that are associated with the nitrogen can shift over to form the following. It can shift over and form a double bond. You got a positively then charged nitrogen and a negatively charged oxygen. And so these things can exist in resonance. And because of that resonance, you're going to see that there's partial single bond character between this carbon and oxygen and partial double bond character located between this nitrogen and carbon. And so because of that partial double bond character exists here, it restricts the rotation that's possible around this bond. Normally for a single bond you can get complete rotation. Well, this you can't. It's locked in place because it's tethered in two positions. And so because of that resonance then we get this kind of special consideration we need to take into account when considering the different degrees of freedom of motion that can happen. And that obviously will impact the three-dimensional structure of a protein if there's certain, because there's peptide bonds located throughout the whole thing, so if you restrict motion through the peptide bond, then that will restrict the number of structures that are possible in a protein. So how do we know that a peptide bond has, in fact, resonance happening? Well, when we take all the measurements of the different things that exist, one thing comes to being. The carbon-oxygen bond here is a little longer than what would be expected for a carbon-oxygen double bond. So, as you may recall, double bonds are shorter than single bonds between two atoms. So if you were to compare them, the carbon-oxygen bond, like in an alcohol, is going to be longer than the carbon-oxygen bond in a double bond. And this is somewhere between the two. So having a longer carbon-oxygen bond is an indication that there is some, I guess you could call it single bond character. And that would certainly be the case when you'd see resonance. Then if you look at this bond here, the carbon-nitrogen bond, this angstroms here that you're measuring the distance is a little shorter than you would anticipate for a typical carbon-nitrogen single bond. So that again is evidence that there is some partial double bond character here. So the upshot of this whole thing is that if you were to kind of box in a plane that connects the alpha carbon to the alpha carbonyl oxygen to the adjacent alpha carbon on the next amino acid to the the alpha amino hydrogen and back to the original alpha carbon again, you can form a little plane. And it turns out that this whole thing, because you don't get any real rotation around this bond because it's locked in place because of the double bond character, then this whole thing moves as a unit, as a plane. It rotates between these two, I guess you could call them fulcrum. What's the plural of fulcrum? Fulcrums? Anyway, these are the points of rotation where this whole thing rotates as one. Imagine rotating a sheet of paper. This rotates as like one unit. There is, and these things are typically pretty planar. Now it turns out I've gone to some talks back some years ago at the American Chemical Society meeting, and there was some indication from some measurements that maybe this wasn't a perfect plane, that there was a little bit of bend in it. But for the purposes of our class and in general discussions, we'll think of this as moving as one big plane, one big unit. So let's back up here. So here's maybe then how you could think of an extended chain. Whoops, I always do that, I hit the wrong button. Here, this whole thing would be a polypeptide chain in its extended form. It might be similar to something like a beta strand, actually. It'd be the closest thing to this, where it's just stretched out. And you can see that in the happiest case scenario, these things, again, rotate as units where these are the middle things. And the most stable configuration that you'll find in an extended chain is having the side chains pointing away from each other. There's the least amount of steric hindrance available there. Now, of course, we've gone over things like alpha helices, beta sheets, and stuff, and so they clearly do all form, so they're not all in this configuration, but other things get involved, as we'll talk about it when we get into some protein filtering discussion. But the main thing that I want you to see here is you can kind of see how these different planes, each peptide bond has its own plane, and the rotation happens around this bond in this direction, around the alpha carbons of each adjacent amino acids. And the trans configuration, so with respect to this, is actually more stable than the cis configuration, with a few exceptions. One of them is we'll see proline can stabilize a cis configuration where you get a instead of having the alternating things, you can kind of go like that. So that's kind of how we talk about it. But this we refer to as a trans configuration where you have the alternating pointing in different directions of the side chains. So these rotations then, they can rotate, and you can, like I say, you can arrange in the trans configuration when the conditions are right and things that could be permitted. But it turns out, though, that, part of the reason for this is, is you can't have rotation around these bonds, so that you're stuck in these planes. So these turn out to be the, how you have to think about how the protein is rotating and forming its three-dimensional configurations. So there's a way to study a protein where we kind of look into that. I mentioned before, here's your alpha carbon, so this is like the point of rotation. So you have one peptide plane rotating here, and on the adjacent amino acid you have another peptide plane, or amide plane, I guess you could call it. These things can be described in how they rotate based on these two bonds. Okay? The rotation around the bond that exists between the alpha carbon and the carbonyl carbon is called the psi rotation. Sometimes I refer to it as the psi angle because we're measuring the angle of rotation that can take place. And the same thing happens between the carbon and the nitrogen, amino nitrogen, the alpha amino nitrogen. That bond, we refer to the rotation around that bond as the phi or phi. So I usually say phi, I don't know why. I guess that could be called phi. Anyway, we have psi and we have phi. Psi is between alpha carbon and the carbonyl carbon, the alpha carbonyl carbon, and the alpha carbon and the alpha amino nitrogen. Sorry, I just yawned. I hope you're not yawning now. Isn't that weird? When people yawn, it makes you yawn. Are you trying not to yawn right now? Anyway, I just distracted myself by yawning. I'll try not to yawn on the video. Just thinking about yawning, though, makes me want to yawn. I hate that. Anyway, back to what we were talking about. So the psi rotation is around the bond between alpha carbon and the alpha carbon carbonyl carbon, and then the alpha carbon and the alpha amino nitrogen, that bond, the rotation is phi. So we can kind of look at these rotations around each amino acid, and for a given amino acid we can kind of plot the probabilities of finding a certain psi and phi rotation angles. Now, one thing you got to keep in mind, it turns out that you can't get a full 360 degree rotation around either of these. What happens is you get some steric clash between, and this is the alpha amino nitrogen hydrogen and the alpha amino carbonyl oxygen, and they clash. So you can't get a full rotation around. So this is the alpha bond, so you can't get full rotation because of these clashes. So you can go 180 in one direction and another 180 in another direction. So you can flip in that direction halfway, you can flick in that direction halfway. Same thing here. You can go 180 in this direction and then 180 in the other direction. So to designate that, one of these directions is called, we treat it just like this, it can go 180, and then in that direction, since it's in the opposite direction, is minus 180. So you'll see that you can have a minus value and a plus value for these psi and phi angles. And what we can then do is think about an entire protein. Think about an entire protein. It's made up of all of these different amino acids, each one having its own peptide plane and each one having its own phi and psi angle. And that allows us to create something called a Ramachandran plot. So one can get a Ramachandran plot by looking at the different psi and phi angles that that can be measured, and they are actually measured for every amino acid in a protein. And because of the fact that we're dealing with all L amino acids in proteins, and there's restrictions about which the amino acids can rotate because of the planar nature of that amide peptide bond, then there is a limit. There is a limit then to what kind of combinations of psi and phi angles can exist. So this would be it for a protein and for amino acids when they. So if one looks at the possibilities and based on the geometric constraints of rotation, you could get this distribution of areas where you're going to find psi and phi angles. So what I'm showing you here in this particular plot is the green, the stuff shaded in green, represents the type of Ramachandran plot that you would see for 18 of the 20 amino acids. And so really the green then, actually I'm going to change the color of my pen so I can actually match it. I'll get close anyway. How do I pick my colors here? I thought I knew how, but apparently I don't. Oh, I know how. It's my other program. Sorry about all my talking. I'm not even making sense right now. Okay, here we go. So the green represents all amino acids except glycine and proline. And so what this means is if you were to look at all the psi and phi angles, those rotations around the different, C alpha to nitrogen or C alpha to carbonyl carbon, you would note that there is a distribution that you'd be able to see for 18 of the amino acids. Now glycine and proline are going to be different than what you see in the green here. All of these represent green. So the blue that you see, the blue represents proline. Now if you remember, proline, if we draw the structure for proline, hopefully you remember the structure for proline. You're in the process of learning the structures. So if you were to look here, so here's the next nitrogen. In fact, I'm going to draw this a slight bit different. So this is going to be an H, and then that's going to be another carbonyl, right? So if I were to look here, proline side chain, if you remember, it goes 1, 2, 3, 4. So it loops around. So this is the right here is this. Let me change the color here. Here's the psi angle, and here's the phi bond, where the rotation takes apart. So if you look here, essentially proline can rotate much like what you see for the green in terms of the psi angles. Where there's problems and a lot more restriction comes from this phi angle, and the phi angle is the one that's tethered by a series of bonds. So this is going to be greatly restricted, and you can see here's the blue part of proline. It's much more restricted, and in fact there's no proline that you'll find in this whole area here. And then there's glycine. Glycine's another, this one's different, and glycine's really not represented here, and that's because if you think about glycine side chain, it's actually, I'll draw glycine side chain, it's an H, that's it. So it has hardly any constraints. So you'll find glycine here, 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 and here. So glycine is actually distributed throughout the entire Ramachandran plot. So it doesn't have a lot of the constraints. So, okay, so what does this do for us? Well, it does a few things for us. It helps us, one, understand the restrictions and mobility restrictions, not mobility, flexibility in terms of forming and adopting different configurations and conformations is limited, and this kind of helps us see from these psi and phi angles. But The other thing we can see is we can kind of see a picture of where the different secondary structures are located, and it actually gives us an understanding why there are kind of just a few secondary structures that can be formed. Largely, that's because the orientations and the restrictions in those orientations as a result of the planar nature of the peptide bond restrict the number of possibilities. So in this region, when you look at beta sheets, for instance, this is parallel and anti-parallel beta sheets, and you measure the corresponding rotations around the psi and phi rotation angles, you'll see that in this quadrant right here, somewhere say between 180 and about 90 is where you're going to find in terms of psi angles, that's where you're going to find your beta sheets. Boy, I make a mess of that. I'm going to get rid of that again. And then, so here's where you're finding, whoops. So this is the region where you're finding your beta sheets right in here. So between 180 and 90 will be your psi rotation, and then if you kind of drop down here, is about 160 and say 60. So between 160 and 60 is where you're going. Well, maybe not 60. I got a little too excited there. Between 160 and say whatever that is. What is that? 120 will be your is that 120 or 140? No, that's 120. 160, 180. Got it. Sorry, I have trouble sometimes. So anyway, in just this region is where you're going to find the beta sheets. In this region is where you're going to find your alpha helices. C here is the collagen helix. And you can read about collagen in your book. I didn't really get into it in any detail, but the collagen is actually pretty interesting. Collagen has the collagen has some secondary structures that we haven't really talked about. The collagen helix, and then the collagen, when you start getting at the different levels of structure, it's kind of tricky because there's a lot of inner overlap between the different structures. The secondary structure is driven by the tertiary structure, and the tertiary structure and quaternary structure are kind of hard to distinguish as well. So it's actually interesting protein as a result. Anyway, collagen helices, when you measure the psi angles and the phi angles, that's where you're going to find collagen. And then we have, this is an alpha helix, but it's a left-handed alpha helix. And somewheres in here you'll see the pi helix and some of the other 310 helix and some of these other things will also have different psi and phi angles. And so essentially, in these are the areas where you're going to find, you're going to find the different secondary structural elements. And then, there'll be other coils and other things like that are going to be laced throughout. Now, a few things that I want you to think about here is what happens if, for some reason, you see a threonine and it shows up out here. What does that mean? That's kind of a forbidden thing. You shouldn't find a threonine out there because threonine should be anywhere on this. Theoretically, you'll find it in the green regions of the Ramachandran plot. So if something's out there, or out here, or out here, well, one way in which Ramachandran plots are used is to evaluate how good a 3D crystal structure or structured protein structure is. So when we get into how you actually solve a crystal structure and dealing with protein structure, you'll see that you're really just generating a 3D model, and the model is fit to some data. And if your model's good, you shouldn't see a whole lot of amino acids that are located in these so-called forbidden regions. But you might see one every now and then. And it may just be a mistake or a poorly determined part of your three-dimensional structure, or maybe that amino acid is kind of forced into a very non-favorable energetically speaking configuration, but it can do so because all the other amino acids stabilize it. It pays the sort of energetic price for having something in a very energetically unstable, I just made up a word, unstable configuration. So if all the other proteins, all the other amino acids in the protein are arranged in such a way that they're at their lowest energy level, and by just having one or two of these in maybe a really not a good, sterically unfavorable orientation, that the gain in energy by having all the other amino acids in a lower energy state might pay for having one or two of these in the outer skirts. But usually people use this to test how good their structural model is. The more of these amino acids that fly out into these forbidden regions, the less likely your 3D model is actually good. And so you got to look at that. So that's one way that people assess the quality of the 3D protein that they're studying, 3D structure. Okay, so moving on here. Let's see, what else did I want to say? So going back to proline. Proline, because it has such restriction in the way that it can rotate, can actually be disruptive to a secondary structure. Sometimes people refer to prolines as helix breakers. I call it kinky, because actually in the case of proline, it's one of the cases where it can stabilize the cis configuration of a, and so instead of a amino acid arrangement, so you can stabilize the cis of the polypeptide backbone. And so by doing that, that would create a bend or a kink in the alpha helix, for instance, or the beta strand. And that would lead to a potential loss of secondary structure, of those secondary structures. So imagine if you had an alpha helix that had no prolines in it, but through maybe a genetic mistake or a mutation, somehow that got introduced, that could cause a pretty huge structural defect by putting a proline where it wasn't before. So prolines can be very destructive to structures because of that kinkiness and the restriction in movement. They can prevent needed movements. So if you have a proline that gets accidentally mutated into a secondary structure, it can really screw up the protein. And if you screw up the protein structure, you'll screw up the protein function. And if you screw up a protein function, you can screw up a metabolic process. And if you screw up a metabolic process, you can screw up an organism. And that leads to a pathology, a disease of some kind. And so it doesn't take much. So something like that would be pretty dramatic, actually. Glycines can have a similar effect, but for a different reason. They can be disruptive to secondary structures, but not because they're restrictive, but because they're so promiscuous. They can rotate any direction they want. And so they do. And so if you add more degrees of freedom, that's a favorable entropy type of thing where it can now address many more degrees of freedom. That can actually be destructive to a protein structure too, because now it can adopt other structures that it otherwise couldn't. So if you have the introduction of a glycine where it normally wasn't, that can actually have catastrophic effect, has the potential to anyway. Not as bad as a proline, however. So you put in these, so the glycines, because of that, they can occupy. So let's look at occupy different regions of the Ramachandran plot. So let's look at a few Ramachandran plots, for real. So what I wanted you to see here, there's a few Ramachandran plots. This first one here is the Ramachandran plot that is And this isn't just any old Ramachandran plot. This is, you go in, you study a whole bunch of different structures, protein structures, and you measure the corresponding sin-phi angles, and this is what you find. Glycine is all over the map. It looks like a shotgun pattern. So because it has so many different degrees of freedom, it's quite a bit different. Then what we see here is what is known as preproline. So preproline is looking at, so let's look at that. So if this is proline, right here, you can see this is proline, then the amino acid just before it is preproline. So having a proline here actually can restrict quite a bit the Ramachandran plot, the Ramachandran of the whatever preproline would be. So you can see it. Even the proline here can restrict what kind of phi and psi angles are present. So here's, again, a bunch of proteins were sampled from known structures, and you can kind of see where the different amino acids that are right in front of proline exist. So this is greatly reduced compared to what we'd expect. We'd expect a lot more in this region. We'd expect much more findings in this region. We would expect much more. Well, maybe this part's about right. And then here's proline. Proline, as we mentioned before, is greatly restricted. It's restricted right here, and there's nothing here. And that's because you can't get rotation around this phi bond. You have very restricted because it's tethered. It just can't go wherever it wants to. So the peptide bond, because it has this resonance and partial double bond character, it can't rotate around the carbon-nitrogen bond of the peptide, and that has implications in terms of the structural configurations that a peptide backbone, that C-alpha chain, can adopt. And so we can study that looking at a few things, but the Ramachandran plot's one way that we can view, so to speak, a protein structure just simply by looking at its ability to rotate around the different bonds on either side of the alpha carbon. And from that, we get a picture of why there are just not an unlimited number of secondary structures that we're going to find in proteins. It's limited because of the geometry.